In this video, we're going to look at the unit circle sine and cosine functions. In particular, we are going to find the values for sine and cosine for the pi over 6, pi over 3, pi over 4, or the 30, 45, 60 degrees, as well as actually the 0, the pi over 2, or in other words, 0 and 90 degrees. We're going to look at the quadrantal angles as well in this video. We're going to identify the domain and range of sine and cosine functions. We're going to introduce a Pythagorean identity for trigonometric functions, and we're going to use reference angles to evaluate trigonometric functions. We're going to start by defining sine and cosine. Now, you probably learned SOHCAHTOA in your previous math courses. SOHCAHTOA isn't a bad way to start learning and defining sine and cosine and all the rest of the trig functions, but we're going to start walking away from that. We're going to start using different definitions, more involved definitions, and especially you're going to see in your math life as you move up in math courses, the definition that you receive in one class gets redefined, tweaked a little, made better, based on your own math understanding. And that's what's going to happen here. Because SOHCAHTOA only works for right triangles, and most of our trig that we are going to be doing in this class is not right triangles, we're going to redefine sine and cosine. And it won't be in terms of opposite over hypotenuse or anything like that, but it'll still be in terms of a ratio. So let's start by building a circle centered at the origin. The distance from the origin to a point on the circumference of the circle xy is the radius, so that's nothing new. And if we define it in terms of the distance formula, where our initial point is 0, 0, we end up with r squared is equal to x squared plus y squared. Now, the angle that we are going to look at will be the angle that's in standard position and whose terminal side will go through some ordered pair xy, which is, of course, on the circumference of the circle. And the way that we're going to define sine now is the ratio. It's still going to be a ratio, but it's going to be the ratio of the y value of that ordered pair divided by the radius. So sine of my angle alpha will be y over r. Similarly, we will do the cosine as the x value over r. So if I'm asked to find the sine of an angle, if I'm given the ratio of the cosine of the angle, then I know that since the cosine of any angle is defined as the x value over the r value, if this is equal to negative 1 over 7, that tells me my x must be the negative part, because my radius can never be negative at this point, and my r must be the 7. Now we know that sine is defined as the y value over the r value, and we have to pay attention to which quadrant we're in to make sure that when we find the y value, we choose either the positive or negative based on the quadrant that the angle's terminal side is in. And in fact, they're telling me that pi over 2 is less than alpha, which is less than pi. That tells me my terminal side will land me in quadrant number 2. So this is pi over 2, and here is pi. That means my angle alpha is in that quadrant number 2. So we know that r squared is equal to x squared plus y squared all day long. So then y squared must be equal to not square root, must be equal to r squared minus x squared. So that means y is equal to plus and minus r squared minus x squared. Now, the simple fact that we know that we are in quadrant number 2, we know that y happens to be a positive value in quadrant number 2, so we end up choosing the positive. I know what r is, I know what x is, so then y must be the square root of 7 squared, because remember, that's my r, and then minus the negative 1 squared, because that was my x. So my y value is going to be the square root of 49 minus 1, so my y value is the square root of 48. So then the sine of my angle is my y value, the square root of 48, over my r value, which happens to be 7. And that's my answer. It is a ratio of the y value over the r value. For For this second example, we're asked to find the cosine and they're giving us the sine. Now we know we just did the sine of my angle alpha, which is -3/4, is equal to the y value over the r value. That means y must be the negative and r must be the positive 4. And using this r squared is equal to x squared plus y squared all day long, if we solve for x squared, we're going to have x squared is equal to r squared minus y squared. That means x is equal to plus and minus r squared minus y squared. Now, x, we're in quadrant number 3. Quadrant number 3. If I were to draw a quick little sketch here, quadrant number 3 means I am landing down here in quadrant number 3. This is where alpha lands, quadrant number 3. That tells me here I'm going to take the negative because we know that x is negative in that quadrant, so it'll be the negative square root. So x is going to be equal to the negative square root of my 4 squared minus my -3 squared. So this x is going to be equal to, let me just erase that because we don't need that anymore. My x is going to be equal to the negative square root of 16 minus 9, which gives me the negative square root of 7. So my sine, or not my sine, we're looking for cosine on this one. My cosine of my angle is negative square root of 7 over my radius, which was 4. And that is my answer. I am not asking for the angle. I am asking for the ratio. And so if you are taking notes here, make sure that you have wrote down this, and the other important bit is this. So though right now as you're taking notes, these are terribly, terribly important. And we're going to keep going back in terms of sine and cosine being x, y, r ratios. Now if we go to a unit circle, so we redo this whole thing with the unit circle. Then on the unit circle, my radius is 1. It's still centered at the origin, but now my radius is 1. Now, if we use the arc length formula, and we talked about this in our last video, we're gonna why do we ignore the radians when we're on the unit circle? Well, since the arc length is my radius times my angle alpha in radians, since my radius is 1, my arc length, which is a length, is equal to the angle in radians. So if I'm talking about the angle, I'm going to make sure I have radians on there. But if I'm talking about it in terms of the arc length on the unit circle, I talk about my units not being in radians, but whatever my unit of length is for my unit circle. So my unit circle could be 1 mile. My unit circle could have a radius of 1 centimeter. So in that case, my arc length would be in centimeters or miles or whatever my 1 unit is. But if I'm talking about the angle, then the angle would have radians attached to it. That's just a little side note. That means, going back to where we really were talking about, was the sine of alpha being y over r. The sine of alpha on the unit circle ends up just becoming the y part of the ordered pair. Similarly, the cosine of alpha, which is x over r on the unit circle, just becomes the x part of the unit circle. So we get this. We say, okay, if we have a radius of 1 now, before we just said any radius, but a radius of 1, the x part becomes the value of the cosine of that angle, and the y part becomes the sine value of that angle. We're going to really, really, really pay attention to this in Chapter 6 when we start drawing the sine and cosine waves as functions, as well as all the rest of the trig functions. But right now, we're going to use the fact that we have x is the cosine value on the unit circle and y is the sine value of that angle on the unit circle. So I am asked to find the sine and cosine values on the unit circle. We're assuming we're on the unit circle. Then the sine of my angle t, because this is my angle t, is the y part. So this is going to be 1/2. The cosine of my angle t is going to be the negative square root of 3/2. Looking at this angle t on the unit circle, my sine of t on the unit circle is going to be the negative square root of 2 over 2, and the cosine of t on my unit circle is going to be the positive square root of 2 over 2. That brings us to the fact that if we have x squared plus y squared is equal to r squared, and we're using the unit circle, then x squared plus y squared is equal to 1. Also, since x is equal to cosine theta and y is equal to sine theta, doing that replacement, if I square both sides, x squared and then cosine squared, and y squared is equal to sine squared, then we have cosine squared of the angle plus sine squared of the angle is equal to 1. And in particular, we call this the identity, the Pythagorean identity. So this is another one that's really important, and it's going to be somewhat a foundational identity that we're going to use throughout this entire class. In fact, throughout all of calculus as well, we'll use a lot of that Pythagorean identity. So make sure that you ask good questions in class if you're not sure how that came about. Now let's talk about specific angles. We're going to first start with a 45, 45, 90, or in other words, the pi over 4, or pi over 2 triangle. This is an isosceles triangle. That means if that's 45 degrees, this is also 45 degrees, and this is 90, or pi over 4, and pi over 2. Because this is an isosceles triangle, that y is equal to x, that means x is equal to y, because those sides have to be the same if the angles 45 and 45 match, and they clearly do. So we know that x squared plus y squared is equal to r squared all day long. In particular, for this, we have x squared and y squared gets replaced with x squared because they are the same value for this particular triangle, and we're on the unit circle, so this equals 1 squared, or just 1. So 2x squared is equal to 1. Dividing both sides by 1 by 2, I get 1/2, taking the square root. In quadrant 1, I'm just going to have the positive instead of the positive and negative. So I get x is equal to 1/2. If I distribute the square root on the numerator and the denominator separately, I'm going to get 1 over the square root of 2. If I rationalize the denominator, I have the square root of 2 over 2. So you may see it in this form, or you may see it in that form. And that tells me that when this is 45, the cosine of 45 degrees is going to be the square root of 2 over 2, which is the same thing as the sine of 45 degrees. Or if you'd rather, the cosine of pi over 4 equals the sine of pi over 4, which equals the square root of 2 over 2. So now we found our first exact value for the pi over 4. What we're going to do now is we're going to look at the 30, 60, 90, or the pi over 6, pi over 3, pi over 2 triangle. And what we do is we first start out with drawing the equilateral triangle, where the radius is 1 here. That means this radius is 1 here, and that means this distance is also equal to 1. Now you said, but I just said I'm going to do the 30, 60, 90, and I just did a 60, 60, 60. Well, that's okay. We're going to go ahead and say, well, if that entire distance is 1, if I cut this triangle directly in half so that this line that I cut it with is perpendicular to that side, that brings me to the 30, 60, 90, and that means this side is worth 1/2. If that side is worth 1/2, that tells me that I have my y value. So, and this angle, instead of being 30, is now 60. So I have, again, r squared is equal to x squared plus y squared. R squared happens to be 1 squared, which is just 1. And then I have x squared, and then I have 1/2, because that's my y value, the quantity squared. Bringing the 1/4, because that's what 1/2 is, squared to the other side of the equal sign, I'll get 1 minus 1/4 is equal to x squared. Before I take the square root of this, I'm going to go ahead and combine this as a single fraction, and it ends up becoming 3 over 4 is equal to x squared. So I'm going to take the square root of both sides, square root of 3 over 4, and of course we are in the first quadrant, so that makes that a positive. I don't have to worry about the plus and minus, it is a positive. I'm going to distribute the square root in the numerator and the denominator, so the square root of 3 over the square root of 4, which is just 2. And so I have found my x value. So my ordered pair, which is x comma y, for the angle that is pi over 6 or 30 degrees, is going to be equal to the square root of 3 over 2 comma 1/2. That tells me that the cosine of pi over 6 or 30 degrees and the sine of pi over 6 or 30 degrees are these values. Here's what the cosine is, and here is what the sine is. Now, if we make a triangle, an equilateral triangle, in which it's formed up here, then we are going to get the fact that this is 1/2 away. If I go ahead and cut that in half, just like I did with the triangle that I started out with, and then that makes this 30 degrees. I'm just going to erase a little bit of this because it's getting a little messy. Now, when I do that, that tells me that this angle that is remaining must be 60 degrees or pi over 3. This ordered pair then, up here, just like I would have done this before, just like I did it here, that ordered pair, my xy, is going to be 1/2 for the x and the square root of 3 over 2. So that tells me that if I'm looking at the 60 degree or pi over 3, the cosine of pi over 3 is going to be 1/2, and then the sine of pi over 3 is going to be the square root of 3 over 2. Now, we now have all of the angles that are in the first quadrant, give or take. Now, we haven't talked about the quadrantal angles, so let's go ahead and talk about the quadrantal angles. If I'm sitting at a radius of 1 on the x-axis, that means I must be 1, 0. So now I have the values for sine and cosine for 0, 360, and 2 pi. If I am straight up, which is 90 or pi over 2, it has a radius of 1, so it must be going through the point 0, 1. That means I have the sine and cosine for pi over 2 or 90 degrees. So now I've found 2 of the quadrantal angles and the 30, 45, 60 as well. Or in other words, 0, pi over 6, pi over 4, pi over 3, and pi over 2. If I'm asked to find the exact values of angles that are ones that we have so far found, I can go right to my unit circle in the first quadrant and just say, okay, I want the sine of pi over 3. If I want the sine of pi over 3, then I'm going to go to pi over 3, which is right here, and I'm going to choose my y value. So this is going to be the square root of 3 over 2. If I am asked to find the cosine of pi over 4, I'm going to go to pi over 4, and I'm going to choose the x value, which is the square root of 2 over 2. Now, if you notice that the sine of pi over 6 is equal to the cosine of pi over 3, this will always be true when the two angles, alpha and beta, two angles, add up to pi over 2 or pi over 90 degrees. So this is something else that you might want to write in your notes because this will be important, really important. Now, because the angles that are negative and the angles that are positive can still be graphed on the unit circle, right? So I know that negative angles is just a negative rotation. Angles larger than pi over 2 is just more than one rotation. And when I'm on the unit circle, all the values for x, y, and r are real values. There's no lower limit for the angle I can put in. That means and there's no upper limit. That means I can put in any angle I want for sine and cosine. That means my input, because of coterminal and reference angles of the sine and cosine functions, when we start to graph these sine and cosine waves, will make more sense, is always going to be the rotation from the positive x-axis. We know the domain of our angle. I'm going to use x as a dummy variable. X is not x. X is just a dummy variable for my angle. The cosine of my angle is going to be any real number. So in other words, my domain of cosine is any real number. And then the sine of the domain of my cosine is also any real number. And you think of it, wait a minute, she just said angles. What? Remember that the arc length on the unit circle is equal to the angle. So I can go from thinking these as 3 radians, or I can think of this as 3, x being my not no longer an angle, but an input of 3. I know, it's like, what? It'll make more sense as we go along. Trust me, it'll start to make more sense. However, since we are on the unit circle, the largest value that sine and cosine will ever take on as an output is 1 and -1. So that gives me my range. The range of cosine is going to run between -1 and 1, and the range of sine, the outputs at most, are going to be -1 and 1. And if you're thinking, what about the ratio of sine when we're not on the unit circle? How does that change that? What happens if I'm not on the unit circle? Is my domain and range still going to be the same? Well, the domain is cool. We're cool. Let's talk about the range. Now, here I'm asked to find the sine of beta. I'm not asking for the angle. I'm asking for the sine of beta, who's in standard position, and the terminal side goes through 3, 3. Now, remember, the sine of beta is defined as my y value over my r value. I have my y value right here. Here's my y value. I don't have my r value, but remember, I can find r squared is equal to the x squared plus the y squared all day long. So my r squared is going to be equal to my x, which is 3, plus my y, which is 3, both of those squared. And so my r squared is going to be 9 plus 9, and so r is going to be equal to the square root. Usually I put on plus and minus, but radius will not take on the plus and minus, of 18. Well, this is the same thing as the square root of 2 times 9, which is the same thing as 3, the square root of 2. So then this must be equal to my y value, which is 3 over 3 root 2, which is 1 over root 2, which we know if we rationalize becomes the square root of 2 over 2. Oh, so I didn't ask for beta, but I know what it is. If my sine value is a square root of 2 over 2, that means my beta must have been pi over 4. Notice my radius, however, is not the unit circle. So at most, my sine and cosine, without transformations, and we're going to go through that in chapter 6, without transformations, at most, my sine is going to take on a value, its ratio is going to take on a value of 1 at the very least without transformations. I'm talking about vertical stretches or vertical movement up or down or compressions. Without transformations, the most my ratios are going to take on for sine and cosine is -1 and 1. So that's my range, and that will be important later, especially when we do inverses. That is all you're going to get. Now, we're going to go back to reference angles, and if you remember with reference angles, it is the shortest distance to the x-axis, and we all know that the ratios of x, y, r are going to be maintained for sine and cosine, whether we're on the unit circle or not on the unit circle, but we're going to focus on the unit circle because we get some really nice values for those known angles. If we go back to the unit circle and we look at our angle T, and our angle alpha, notice that this y value is the same as this y value. So what we find is, and the radius obviously is still the same, the sine of T is going to be the same thing as the sine of alpha. They're going to have the same values. They're on the same ratio values. Now, if we look at in quadrant 1 and 4, here's my y value. Here's the negative y value. And so this angle T and this angle beta. So the sine of T is going to be equal to the negative sine of beta. Or we can say the negative sine of T will equal to the sine of beta. Similarly, if we look at cosine, so if we do the same thing for cosine, So I'm going to look at the cosine of t, which is here. That's this x value. And then this x value, its ratio, because I'm in quadrant number 1 and quadrant number 2, is going to be the negative cosine of alpha. Similarly, quadrant 1 and 4, I have the cosine of t is going to be, well, here's my x value, here's my x value, they are the same. My radius obviously is still 1 because I'm on the unit circle. That means I have the cosine of beta. So what we know then is if I'm in quadrant 1 and 2 for sine, so if I'm in quadrant 1 and 2 for sine, if they have the same y value and the same radius, they will take on those angles that land in quadrant 1 and quadrant 2 will take on the same values. Similarly, if I am in quadrants 3 and 4, if the y values are just opposite signs, then their sine values from quadrant 1, 3, and 4 will just be negatives of the sine value or the ratio in quadrant 1. Cosine. Cosine in quadrants 1 and 4, if my terminal sides are in 1 and 4, and my x values are the same, and my ratios, or my radiuses are the same, then cosine in 1 and 4 will take on the same values for those angles that land in 1 and 4 if their x values are the same. And as with sine, in these two quadrants, we have the negatives of it. That leads us to the fact that we know the sine of t is equal to the sine of alpha, but the sine of t is equal to the negative sine of beta, and same with cosine. Now, we're going to talk about reference angles. Why? Because reference angles and the quadrant we land in is going to help us fill out the rest of the unit circle. And later, it's going to help us evaluate other sine and cosine values when we are not using our special angles. So our special angles are the 0, pi over 6, pi over 4, pi over 3, and pi over 2, and the ones that would be similar to those using reference angles. Reference angle is always the shortest distance from the x-axis to the terminal side. Notice if we're in quadrant 1 and our angle is less than pi over 2, that they are the same value. If we're in quadrant 2 and our angle that we are looking at is between pi over 2 and pi, you find your reference angle by taking the your angle that you're giving and you subtract it from pi. Again, if you're in quadrant number 3 and your angle is between pi and 3 pi over 2, to find its reference angle, it is going to be your angle minus pi. And lastly, if you're in quadrant number 4 and your angle that you are looking for lands in the quadrant number 4 where your angle is between 3 pi over 2 and 2 pi, then your reference angle is going to be 2 pi minus the angle, which will give you your reference angle. So that's where those all come from. Okay, so we want to just find the reference angles here. So if I want to find the reference angles, the first thing I have to do is figure out where I land so I know if I'm adding or subtracting. So this is 180 degrees, this is 90, this is 270, this is 0. I must be landing here. So if I'm landing there, I'm going to take 240 degrees and subtract off 180 degrees, and my reference angle is 60 degrees. That is the shortest distance back to the x-axis as a rotation. If we look at 5 pi over 4, here's half a pi, here's a full pi, here is 1.5 pi's, and here is 2 pi's or 0 pi's. So 5 pi over 4 is bigger than 1 but less than 1.5. So I'm again landing down here. So my reference angle is the shortest distance back. So I'm going to take 5 pi over 4 and I'm going to subtract off 1 pi, which is 5 pi over 4 minus 4 pi over 4. So my reference angle is going to be pi over 4. That is my reference angle. Negative 11 pi over 3, well, 11 pi over 6. Well, okay, so Negative means I'm going in this direction. Right here, one full rotation is going to be 6 pi over 3. So 11 pi over 3, I'm going to have to find a coterminal angle, first of all, because I've done more than one rotation. So I'm going to start out by finding the coterminal. So I take 11 pi over 3, and I'm going to add to it, since I know I've done at least one rotation, let's add 6 pi over 2 to it, or 6 pi over 3, because that is one full rotation. So 6 pi over 3. That's the same thing as adding 2 pi and then having the common denominator. So when I do that, I get negative 5 pi over 3. Oh, so that's a coterminal angle. So, okay, so I've done one full rotation, and then negative 5 pi over 3 is not quite to 5 pi, or 6 pi over 3, so that means I must be landing here. Here's where I land. So if I take this negative 5 pi over 3 and I add to it 2 pi, which is the same thing as negative 5 pi over 3 plus 6 pi over 3, I'm going to get a coterminal angle. My coterminal angle is pi over 3. That just happens to be the same thing as my reference angle, because remember, if I'm in quadrant number 1 and my angle is less than pi over 2 but bigger than 0, my reference angle is my angle. So I found my reference angle. Now, once we found our first major pi over 6, pi over 4, pi over 3 angles, as well as the 0 and the pi over 2, I can fill in the rest of my unit circle. So if this has a reference angle of pi over 6, and this has a reference angle of pi over 6, and this has a reference angle of pi over 6, and this has a reference angle of pi over 6, all of these values will be the same for the x and y, but with the appropriate negative sign attached to them. Similarly, if I am talking about the pi over 4, this also has a reference angle of pi over 4, and this one, and this one. So all of these will have the same x and y values with the appropriate negative attached to them. Lastly, the pi over 3, pi over 3, pi over 3, pi over 3, all of these will have the same values with the appropriate negative attached to them. So basically, oh wait, I just haven't done the quadrantal. Notice this one and this one have opposite signs, and this one have opposite signs for the 1 and the negative 1. The zeros are still in the same positions, but it's either 1 or negative 1, depending on the quadrantal. So basically, here's the deal. If you know this one, and this one, and this one, you know all the way around the unit circle by reference angles. So that's kind of cool. So here's how to, given an angle between 0 and 2 pi, how to find its reference angles. Now we're asked to find the exact values. So I have the sine of 150, and I'm going to use reference angles to do this. So the reference angle of 150, the way I'm going to find it is I'm going to take 180, I'm going to subtract off 150, and I'm going to get an answer of 30 degrees. So this is the same thing as the sine of 30 degrees. I'm going to go up to my unit circle here, and I'm going to look for 30 degrees. The sine of 30 degrees is 1/2. Because I'm in quadrant number 2, and sine has a positive y value in that quadrant, it is just going to be simply pi over 2. Now, for cosine 11 pi over 3, we just found its reference angle. It's pi over 3. So this is going to be the same thing as the cosine of pi over 3. So I'm going to go to pi over 3 on my unit circle. Pi over 3 is here. Cosine is 1/2. So my answer for this is 1/2. Now I'm going to do the 7 pi over 3. So I'm going to take 7 pi over 3. I'm going to find its reference angle. 7 pi over 3 is in quadrant number 4. Its reference angle, so I'm going to take 7 pi over 4, and I'm going to subtract it from, actually I'm going to do 2 pi subtracting 7 pi over 4. So 2 pi minus 7 pi over 4 is equal to 8 pi over 4. So we have the same common denominator. So its reference angle is pi over 4. So this is the same thing as the negative. And you're thinking, why negative? Well, because down in quadrant number 4, the y value would be negative. So it's going to be the negative, the sine of pi over 4, which is a negative square root of 2 over 2. And so I found my exact values using reference angles, and I actually didn't have to really go to any of the other angles besides using the first quadrant and using reference angles and using the first quadrant. Now, I totally could have done C by going over here and say, where's 7 pi over 4? Well, here's 7 pi over 4, and here is my y value associated with 7 pi over 4 on the unit circle. So I could have done that as well. So I can do it with reference angles, or if I have my unit circle in front of me, as long as it lands on the unit circle, then I can just find that value from the unit circle. And that's it for this video. In the next video, we're going to hit all the rest of the trig functions. So look forward to that, and we will see you in class. Be sure to ask good questions.